Welcome back to Basic Mathematics. Differential Calculus Part 2. Derivation of trigonometric functions by first principle. Derived function. Let us define derived function. Derived function or derivative is defined as the instantaneous rate of change. Derived function is a tool to quantify the change in a function of a variable, say x, with respect to its input variable x at a certain value of the variable x. Derived function or derivative is the slope of the tangent line at that point on the graph of the function. Please note, the derived function or the derivative can be defined as the ratio of the instantaneous change in the dependent variable to that of the independent variable. The process of finding a derivative of a function is called differentiation. Differentiation. Differentiation is the process of finding a derivative or the slope of the tangent line at that point or at the point of interest on the graph of the function. To draw a line, we need 2 points. One is the point of interest, and another point we consider is nearest to it. From the coordinate geometry, we know how to find the slope of the line. Slope formula. Let's take 2 points on a graph, point A and point B. Remember, from the coordinate geometry, the slope of the point A, x1, y1, from point B, x2, y2. The slope m of the point A to the point B is defined as height is divided by distance equals AC divided by BC. The slope m equals AC divided by BC equals y1 minus y2 divided by x1 minus x2 equals difference between y coordinates of 2 points divided by difference of x coordinates of those 2 points. Linear function and slope. See a line on a graph. Y equals mx plus c. If a function of a variable is linear, then the function can be written in slope-intercept form as y equals mx plus c, where m is the slope or the gradient of the line. We defines the gradient as derived function of y and denoted as dy dx equals m. nonlinear function. See on a graph. We draw a very simple curve of y equals x squared. For a nonlinear function, we can find out the slope of the tangent at the point of interest, x, y, to calculate the slope of a function, y equals x squared, at a point P, x, y. Let's take next point Q at a small interval of h on x-axis. The coordinates of Q are x plus h, y plus k. The value of y plus k equals x plus h whole squared comes from the curve equation. Therefore the increase in y, k equals x plus h whole squared minus x squared equals x squared plus 2xh plus h squared minus x squared equals 2xh plus h squared. An increase in x equals h. Therefore slope at x, y equals k divided by h equals 2 times xh plus h squared divided by h equals 2x plus h. This slope here is the slope of a secant passing through the points P, x, y, and Q, x plus h, y plus k. Now, considering h is very small and approaching to 0, or h tends to 0, we are converging 2 points to 1. By this approach of h tends to 0, we convert the secant into the tangent. Hence, h in the expression can be ignored, or h equals 0, and slope is 2x. The slope of y equals x squared. dy dx equals 2x. Derived function. The basic difference is the slope of a secant gives us the average rate of change between 2 points, and the slope of the tangent gives the instantaneous rate of change, which is the basic definition of derived function or derivative. For a continuous function, y equals function f of x, we deduced that the instantaneous rate of change at a point P, x, y, is given by function of x plus h minus function f of x whole divided by h, where h is taken very small increment, or almost 0, or can say h approaches or tends to 0. Delta method and the slope. This algebraic method of adding a small quantity h to calculate the slope of the tangent is known as delta method. The derived function or derivative is referred as by first principle, or for function of a variable y equals f x. Therefore derivative f dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h. Please note, f dashed is often used for derivative dy dx. Derivative by first principle. Now we will apply delta method to explore various functions of x, or function f of x, using algebraic method of adding a small quantity h to x coordinate and corresponding increment k to y coordinate. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h. In our other video, which is referred here, we have discussed many cases in detail. Here we will take some important cases only. Derivative by first principle. Let's take simple quadratic function f x equals y equals x squared. Start by first evaluating function of x plus h minus function f of x. That is, x plus h squared minus x squared equals x squared plus 2xh plus h squared minus x squared equals h times 2x plus h. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h equals limit h tends to 0, h times 2x plus h divided by h equals limit h tends to 0, 2x plus h. Note, h is not equals 0. The limit of the gradient as h tends to 0 is 2x. Therefore derivative that is dy dx equals 2x. Derivative of x to the power of n. By first principle, take a function f of x equals y equals x to the power of n. We start by first evaluating function of x plus h minus function f of x. That is, x plus h to the power of n minus x to the power of n. Remember, x plus h to the power of n equals x to the power of n plus nx to the power of n minus 1h plus 1/2 n, n1, x to the power of n minus 2h squared plus nxh to the power of n minus 1 plus h to the power of n. Therefore x plus h to the power of n minus x to the power of n equals x to the power of n plus nx to the power of n minus 1h plus 1/2 n, n1, x to the power of n minus 2h squared plus nxh to the power of n minus 1 plus h to the power of n minus x to the power of n. F dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h equals limit h tends to 0, h times n times x to the power of n minus 1 plus 1/2 n times n1 times x to the power of n minus 2 times h plus h to the power of n minus 1 divided by h equals limit h tends to 0, nx to the power of n minus 1 plus 1/2 n times n1 x to the power of n minus 2 times h plus h to the power of n minus 1, h not equals 0. The limit of the gradient h tends to 0 is n times x to the power of n minus 1. Terms containing h will be equals 0. Therefore derivative f dashed x to the power of n equals d dx x to the power of n equals n times x to the power of n minus 1. Derivative of 1 divided by x. Let's take another function f x equals y equals 1 divided by x. Evaluating function of x plus h minus function f of x. That is, 1 divided by x plus h minus 1 divided by x. Or solving the fraction by LCM method. Equals x minus h divided by x times x plus h. Equals minus h divided by x times x plus h. f dash of x equals dy dx equals limit h tends to 0, function of x plus h, minus function f of x whole divided by h, equals limit h tends to 0, minus h divided by x times x plus h whole divided by h, equals limit h tends to 0, minus 1 divided by x square plus x times h. Note here, h is not equals 0. The limit of the gradient as h0 is minus 1 divided by x square. Terms containing h are equals 0. Therefore derivative d dx 1 divided by x equals minus 1 divided by x squared. Derivative of 1 divided by square root of x. Let's take another function f, x equals y equals 1 divided by square root of x. Evaluating function of x plus h minus function f of x. That is, 1 divided by square root of x plus h minus 1 divided by square root of x. Or solving the fraction by LCM method. Equals square root of x minus square root of x plus h. Whole divided by square root of x times square root of x plus h. To solve, we need to multiply and divide by a factor of square root of x plus square root of x plus h. Function of x plus h minus function f of x equals square root of x minus square root of x plus h. Whole divided by square root of x times square root of x plus h times square root of x plus square root of x plus h. Whole divided by square root of x plus square root of x plus h. Use the identity a plus b times a minus b equals a square minus b square. Therefore, equals x minus h whole divided by square root of x times square root of x plus h times square root of x plus square root of x plus h equals minus h whole divided by square root of x times square root of x plus h times square root of x plus square root of x plus h. f dash of x equals dy dx equals limit h tends to 0, function of x plus h minus function f of x whole divided by h equals limit h tends to 0 in bracket minus h divided by square root of x times square root of x plus h times in bracket square root of x plus square root of x plus h whole divided by h equals limit h tends to 0 in bracket minus 1 divided by square root of x times square root of x plus h times in bracket square root of x plus square root of x plus h. Note here, h is not equals 0. The limit of the gradient as h0 is minus 1 divided by square root of x times square root of x times in bracket square root of x plus square root of x equals minus 1 divided by 2x times square root of x, as the terms containing h are equals 0. Therefore derivative d dx 1 divided by square root of x equals minus 1 divided by 2x times square root of x. Power rule for differentiation. Finding the derivative from first principles can be tedious. The previous two examples clearly show this. However, using the first principles approach, we produced the results are shown in the table. This power rule can also be written as: if y equals x to the power of n, then dy dx equals n times x to the power of n minus 1. Or if f x equals x to the power of n, then f dashed x to the power of n equals n times x to the power of n minus 1. General rules of derivative. Some general rule of derivatives we have proved are summarized here. Constant function f of constant c, or y equals c, therefore dy dx equals 0. 2. Y equals x, therefore dy dx equals 1. 3. Constant out f dashed of a times x squared equals a times function of x squared equals a times 2x. 4. Plus rule function of u plus v equals f dashed u plus v equals f dashed u plus f dashed v. 5. F dashed x to the power of n equals n times x to the power of n minus 1. 6. D dx 1 divided by x equals minus 1 divided by x squared. 7. D dx 1 divided by square root of x equals minus 1 divided by 2x times square root of x. The product function d dx u times v equals v d dx u plus u dx v. Let u and v are function of x, so u dash of x equals d u dx equals limit h tends to 0, function u of x plus h minus function u f of x whole divided by h. And v dash of x equals d v dx equals limit h tends to 0, function v of x plus h minus function v f of x whole divided by h. Now f u times v equals d dx u times v equals lim h 0 u x plus h v x plus h u x v x whole divided by h. To solve it further, we add and subtract a term u x v x plus h. Therefore d dx u times v equals limit h tends to 0 u x plus h v x plus h minus u x v x plus h plus u x v x plus h minus u x v x whole divided by h. Rearrange the terms and take the common factor out. d dx u times v equals limit h tends to 0 v x plus h times u x plus h minus u x plus u x times v x plus h minus v x whole divided by h. Note in the bracket, by definition, they are the derivative of u and v. Therefore equals limit h tends to 0 v x plus h times u x plus h minus u x whole divided by h plus u x times v x plus h minus v x whole divided by h equals limit h tends to 0 v x plus h times do dx plus u x times dv dx. The limit as h tends to 0. Note now, terms containing h will be equals 0. Therefore derivative d dx u times v equals v x times do dx plus u x times dv dx. Quotient rule. d or dx u divided by v equals v times d or dx u minus u times d or dx v divided by v square. Let u and v are function of x, so u dash of x equals du dx equals limit h tends to 0, function u of x plus h minus function u f of x whole divided by h. And v dash of x equals dv dx equals limit h tends to 0, function v of x plus h minus function v f of x whole divided by h. Now, f u divided by v equals d o dx u divided by v equals limit h tends to 0, u x plus h divided by v x plus h u x divided by v x whole divided by h. Rewrite f u divided by v equals d o dx u divided by v equals limit h tends to 0, 1 divided by h in bracket function u of x plus h divided by function v of x plus h minus function u of x divided by function v of x d dx u divided by v equals limit h tends to 0, 1 divided by h in bracket function u of x plus h times function v of x minus function u of x times function v of x plus h whole divided by function v of x plus h times function v of x. Solve it further. In numerator, we add and subtract a term. Function u of x times function v of x. Therefore, d dx u divided by v equals limit h tends to 0, 1 divided by h. In bracket, u x plus h times v x minus u x times v x plus u x times v x minus u x times v x plus h whole divided by v x plus h times v x. Rearrange and take common factor out. d dx u divided by v equals limit h tends to 0, 1 divided by h in bracket v x times u x plus h minus u x plus u x times v x minus v x plus h whole divided by v x plus h times v x equals limit h tends to 0, in bracket v x times 1 divided by h v x u x plus h minus u x times 1 divided by h times v x plus h minus v x whole divided by v x plus h times v x. Note in the bracket, by definition, they are derivative of u and v. Or d dx u divided by v equals limit h tends to 0, 1 divided by function v of x plus h times function v of x in bracket function v of x times du dx minus function u of x times dv dx. The limit as h tends to 0, terms containing h will be equals 0. Therefore derivative d dx u divided by v equals 1 divided by function v of x times function v of x in bracket function v of x times du dx minus function u of x times dv dx. d dx u divided by v equals in bracket function v of x times du dx minus function u of x times dv dx whole divided by square of function v of x. It is known as quotient rule. Derivative of x to the power of n, where n is a negative. For the sake of completeness, we will generalize the value of n. First extend n from positive to negative n, or setting n equals minus k. For the function f x equals y equals x to the power of n, where n is a negative integer, equals minus k is positive integer, f(x) equals y equals x to the power of n equals x to the power of minus k equals 1 divided by x to the power of k. Using the quotient rule, d dx u divided by v equals v times d dx u minus u times d dx v divided by v square. Here u equals 1, so d dx u equals 0 and v equals x to the power of k, so d dx x to the power of k equals k times x to the power of k minus 1. Using the quotient rule, d dex 1 divided by x to the power of k equals x to the power of k times 0 minus 1 times k x to the power of k minus 1 divided by x to the power of k whole square equals minus 1 times kx to the power of k minus 1 divided by x to the power of 2k equals minus 1 times kx to the power of k minus 1 minus 2k equals minus 1 times kx minus k minus 1. But remember, n equals minus k. So, derivative d dx, x to the power of n minus 1. We have noted that derivative f xn equals d dx, x to the power of n equals nx to the power of n minus 1 is still true for negative integers. Derivative of x to the power of n where n is a fraction. Derivative of y equals x to the power of n where n is a fraction. Or setting n equals p divided by q, both p and q is positive integer. For the function f x equals y equals x to the power of n equals x to the power of p divided by q. Note we raise the whole function to the power of q. We have y to the power of q equals x to the power of p. Next, using implicit differentiation, we differentiate both sides. With respect to x, d dx y to the power of q equals d dx x to the power of p. Therefore q minus 1 dy dx equals px p minus 1, or dy dx equals px to the power of p minus 1, divided by qyto the power of q minus 1. Please note, implicit differentiation is explained little later in the video. dy dx equals px to the power of p minus 1, divided by qy to the power of q minus 1, equals p divided by q, x to the power of p minus 1, divided by y to the power of q minus 1. As y equals x to the power of p divided by q, therefore y to the power of q minus 1 equals x to the power of p divided by q to the power of q minus 1. Equals x to the power of p, q minus 1, divided by q, equals x to the power of p minus p, q. Therefore dy dx sad smiley x to the power of p minus 1, divided by y to the power of q minus 1, equals x to the power of p minus 1, divided by x to the power of p minus p divided by q. Solving further and organizing the power of x equals x to the power of p minus 1 minus p plus p divided by q equals x to the power of p divided by q minus 1. We have the derivative f dashed x to the power of n equals d dx x to the power of n equals d dx x to the power of p divided by q equals p divided by q times x to the power of p divided by q minus 1. So nx to the power of n1 is still true for fractions. Derived function of trigonometric functions. Recollection of basic trigonometry. Trigonometrical ratios, sine, cosine, and tangent. In a right-angled triangle we have sides, longest as hypotenuse, another two as opposite, adjacent. So we define sine equals opposite divided by hypotenuse, cosine equals adjacent divided by hypotenuse, and tangent equals opposite divided by adjacent. Remember, tangent 0 is equal to 0. Slope of the line parallel to x-axis, tangent 45 degree equals 1. Tangent 90 degrees equals infinity. Slope of the line parallel to y-axis. Please also note inverse of these ratios, which are defined as cosec equals 1 divided by sine A, secant or sec equals 1 divided by cosine A, and cotangent or cot equals 1 divided by tangent A. The Pythagoras theorem. Pythagoras' theorem states, in a right-angled triangle, the square on the hypotenuse equals the sum of the squares on the other two sides. Pythagoras' theorem is a square plus b square equals c square. Starting from Pythagoras' theorem is a square plus b square equals c square. We shown here three identities used often in trigonometry. First is sine A square plus cos A square equals 1. Starting from Pythagoras' theorem is a square plus b square equals c square. We shown here the identity. Second is 1 plus cot A square equals cosec A square. Starting from Pythagoras' theorem is a square plus b square equals c square. We shown here the identity. Third is tan A square plus 1 equals sec A square. sine alpha plus beta equals sine alpha cos beta plus cos alpha sine beta. The sine of sum of two angles alpha and beta is equals to the product of the sine of alpha and cosine of beta plus the product of the cosine of alpha and sine of beta. Cos alpha plus beta equals cos alpha cos beta minus cos alpha sine beta. The cosine of sum of two angles alpha and beta is equals to the product of the cosine of alpha and cosine of beta minus the product of the sine of alpha and sine of beta. Tangent alpha plus beta equals tan alpha plus tan beta divided by 1 minus tan alpha tan beta. The tangent of sum of two angles alpha and beta is equals to the sum of the tangent of alpha and tangent of beta overall divided by 1 minus the product of the tangent of alpha and tangent of beta. Here is the summary of double angle. Just replace beta by alpha. Here we remind you that the sine and cosine curves, sine and cosine curve, for angles 0 to 360 degrees. Note carefully. We may use them to explain derivative of sine x by first principle. Derived function by first principle of trigonometric functions. Derivative of sine function sine x. Please note that the variable x is a real number and is given in radian from 0 to pi by 2. 0 less than or equal to x less than or equal to 1/2 pi. Let function sine x equals y equals sine of x. And using the definition from first principle, we have y equals sine of x. F dashed x equals d dx sine x equals limit h tends to 0 sine of x plus h minus sine of x whole divided by h. To solve, we will use the identity sine of a plus b equals sine of a times cos of b plus sine of b times cos of a. We then have d dx sine x equals limit h tends to 0, sine of x times cos of h, plus cos of x times sine of h, minus sine of x whole divided by h, equals limit h tends to 0, sine of x times cos of h, minus sine of x whole divided by h, plus sine of h times cos of x whole divided by h. Take the common factors of sine x and cos x out, equals sine of x times limit h tends to 0, cos of h minus 1 whole divided by h plus cos of x times limit h tends to 0, sine of h divided by h. We now need to determine the value of the limits limit h tends to 0, cos of h minus 1 whole divided by h, and limit h tends to 0, sine of h divided by h. To solve the problems of the limit, we will take help of the graphs of the functions. We start with limit h tends to 0, cos of h minus 1 whole divided by h. As cos 0 is equal to 1, we replace 1 by cos 0. We have that limit h tends to 0, cos of 0 plus h minus cos of 0 whole divided by h, which, by definition, is the gradient of the cosine function cos x at x equals 0. Now follow the graph of cos x, and note the gradient at x equals 0. Its tangent is parallel to x-axis, or m equals 0. Therefore limit h tends to 0, cos of h minus 1 whole divided by h equals 0. Graph of cos x. In this graph of cos x, note the value at x equals 0. The tangent is y equals 1. And slope m, or gradient, is equals 0. We are now left with determining limit h tends to 0, sine of h divided by h. We will use the graph of the function y equals sine of x divided by x. Graphs of sine of x and sine of x divided by x. In this graph of sine of x divided by x, note the value at x equals 0. The tangent is y equals 1. Therefore, limit h tends to 0, sine of h divided by h equals 1. From the graph of y equals sine of x divided by x, it is clear that the value of sine of h divided by h at x equals 0 is 1. Therefore, limit h tends to 0, sine of h divided by h equals 1. F dashed x equals d dx sine of x equals limit h tends to 0, sine of x times cos of h minus 1 whole divided by h, plus cos of x times sine of h divided by h, equals sine of x times limit h tends to 0, cos of h minus 1 whole divided by h, plus cos of x times limit h tends to 0, sine of h divided by h. Now we have the value of the limits. Limit h tends to 0. Cos of h minus 1 whole divided by h equals 0. Limit h tends to 0. Sine of h divided by h equals 1. F dashed x equals d dx sine of x equals 0 plus cos x times 1 equals cos x. Therefore, the derivative f dashed x equals d dx sine of x equals cos x. Derivative of sine function. Using geometry, let us again confirm. Limit h tends to 0, sine of h divided by h equals 1. Please focus on the figure. We are going to draw. In first quadrant of x, y graph, we make 1/4 of a circle of radius of 1. Take a point P on the circle. Note the angle POA equals theta, which form a sector of the circle. Area of the sector, OPA of the circle, is 1/2 theta, as radius r equals 1. Now join the point P to pointer. To make a triangle OPA, drop a perpendicular PB on line OA. The area of OPA equals 1/2 OA times PB equals 1/2 sine theta, as radius OP equals 1. Extend the line OP to the point C, such that a perpendicular to line OA at A will meet at C. It makes a right-angled triangle OAC. Area of this triangle is equals 1/2 OA times PB equals 1/2 tan theta theta, as radius OA equals 1. From the figure, it is clear that the area of OPA, A1, equals 1/2 sine theta, is smaller than the area of the sector OPA, A2, of the circle, which is 1/2 theta. Is smaller than area of this triangle OAC, A3, is equals 1/2 tan theta. Therefore A1 less than A2 less than A3. For 0 less than theta less than 1/2 pi, or therefore 1/2 sine theta less than 1/2 theta less than 1/2 tan theta, or sine theta less than tan theta. Therefore sine theta less than tan theta, or sine theta less than tan theta. Or inverting whole expression, 1 divided by sine theta more than 1 divided by theta more than 1 divided by tan theta. Multiplying all by sine theta. Therefore 1 more than sine theta divided by theta more than cos theta, limit theta tends to 0, cos 0 is equal to 1. Therefore 1 is more than sine h divided by h is more than 1. This implies that as tends to 0 sine h divided by h equals 1. Derivative of cosine function cos x. Please note that the variable x is a real number and is given in radian. Let function x equals y equals cosine of x, and using the definition from first principle, we have the derivative f dashed x equals d dx cosine of x equals limit h tends to 0 cosine of x plus h minus cosine of x whole divided by h. Now make use of the identity. Cosine of a plus b equals cosine of a times cosine of b minus sine of a times sine of b. We have then f dashed x equals d dx cosine of x equals limit h tends to 0 cosine of x cosine of h minus sine of x sine of h minus cosine of x whole divided by h. We have then f dashed x equals d dx cosine of x equals limit h tends to 0 in bracket cosine of x times cosine of h minus cosine of x whole divided by h minus sine of x times sine of h whole divided by h. Take the common factors of sine x and cos x out equals cos x times limit h tends to 0 cos h minus 1 whole divided by h minus sine x times limit h tends to 0 sine of h divided by h. We have the value of the limits. Limit h tends to 0 cos of h minus 1 whole divided by h equals 0 limit h tends to 0 sine of h divided by h equals 1. So the f dashed x equals d dx cosine of x equals 0 minus sine x times 1 equals minus sine x. The derivative f dashed x equals d dx cosine of x equals minus sine x. Derivative of tangent function tan x. For this proof, we use the ratio definition of the tangent. Let function x equals y equals tan x equals sine x divided by cos x, and then make use of the quotient rule. Quotient rule: d dx u divided by v equals v times d dx u minus u times d dx v divided by v squared. So, letting u equals sine x and v equals cos x, d dx u equals d dx sine x equals cos x, and d dx v equals d dx cos x equals minus sine x. So the f dashed x equals d dx tan x equals cosine of x times cosine of x plus sine of x times sine of x divided by cosine squared x equals cosine square of x plus sine square of x divided by cosine squared x equals 1 divided by cosine squared x, as sine square of x plus cosine square of x equals 1. Therefore d dx tan x equals sec squared x. Again, a more formal proof can be obtained by using a first principle approach. Let function x equals y equals tan x equals sine x divided by cos x. Using the definition f dashed x equals d dx tan x equals limit h tends to 0 tan of x plus h minus tan of x whole divided by h equals limit h tends to 0 1 divided by h in bracket sine of x plus h divided by cosine of x plus h, minus sine of x, divided by cosine of x. Solving the fractions of sine and cosine further, equals limit h tends to 0, 1 divided by h in bracket sine of x plus h cosine x minus sine of x cosine of x plus h, divided by cosine of x plus h. To solve, we will use the identity sine of a minus b equals sine of a cos of b minus sine of b cos of a. So we have f dashed x equals d dx tan x equals limit h tends to 0, 1 divided by h in bracket sine of x plus h minus x divided by cosine of x plus h equals limit h tends to 0, 1 divided by h in bracket sine of h divided by cosine of x plus h equals limit h tends to 0, sine of h divided by h in bracket 1 divided by cosine of x plus h. Note h is not equals 0. The limit of the gradient as h tend to 0 is 1 divided by cos square of x. Note the terms containing h are equals 0. Therefore the derivative f dashed x equals d dx tan of x equals 1 divided by cos square of x equals secant square of x. Derivative of cotangent function cot x. For this proof, we use the ratio definition of the cotangent. So f x equals y equals cot x equals cos x divided by sine x, and we make use of the quotient rule. Quotient rule: dr dx u divided by v equals v times dr dx u minus u times dr dx v divided by v squared. So, letting u equals cos x and v equals sine x, dr dx u equals dr dx cos x equals minus sine x, and dr dx v equals dr dx sine x equals cos x. So we have f dashed x equals d dx cot x equals minus sine of x times sine of x minus cosine of x times cosine of x divided by sine squared x equals minus sine square of x plus cosine square of x divided by sine squared x equals minus 1 divided by sine squared x, as sine square of x plus cosine square of x equals 1. Therefore d dx cot x equals minus cosec squared x. Derivative of secant function sec x. For this proof, we use the ratio definition of the secant. So f function x equals y equals sec x equals 1 divided by cos x, and we make use of the quotient rule. Quotient rule: dr dx u divided by v equals v times dr dx u minus u times dr dx v divided by v squared. So, letting u equals 1 and v equals cos x, dr dx u equals 0, dr dx v equals dr dx cos x equals minus sine of x. Therefore we have f dashed x equals d dx secant of x equals minus sine of x times 0 plus 1 times cosine of x divided by cosine squared x equals sine of x divided by cosine square of x. Rewrite it as equals sine of x divided by cosine of x times 1 divided by cosine x equals secant of x times tangent of x. Therefore d dx, cosec of x equals secant of x times tangent of x. Derivative of cosecant function cosec x. For this proof, we use the ratio definition of the cosecant. So f function x equals y equals cosec of x equals 1 divided by sine of x. And then we make use of the quotient rule. Quotient rule. d or dx u divided by v equals v times d or dx u minus u times d or dx v divided by v squared. So, letting u equals 1 and v equals sine x, d or dx u equals 0 and d or dx v equals d or dx sine x equals cos x. So we have f dashed x equals d dx cosec of x equals sine of x times 0 minus 1 times cosine of x divided by sine squared x equals minus cosine of x divided by sine squared x equals minus cosine of x divided by sine x times 1 divided by sine of x equals minus cosec of x times cotangent of x. Therefore d dx cosec of x equals minus cosec of x times cotangent of x. Derivative of trigonometric function. Note function f equals y and derivative f equals dy dx. For the function sine of x the derivative is cosine of x. For the function cosine of x the derivative is minus sine of x. For the function tangent of x the derivative is sec square of x. For the function cot of x the derivative is minus cosec square of x. For the function secant of x the derivative is sec of x times tan of x. For the function cosecant of x the derivative is minus cosec of x times cot of x. Function of a function. When y equals x squared plus 4, we say that y is a function of x. If y equals x squared plus 4 to the power of 5, we say that y is a function, the fifth power, of a function, x squared plus 4 of x. Let a function t, x, equals x squared plus 4. Then y equals t to the power of 5, which is same as y equals x squared plus 4 to the power of 5. In this case, we have used another variable t, which links together the variables y and x. Function of a function. Let y equals f, t, and t equals g, x, and if x changes by a small amount delta x, then the consequent change in t be delta t and the change in y be delta y. We introduce delta t in delta y divided by delta x equals delta y delta t times delta t divided by delta x. As delta x tend to 0, so also delta t tend to 0 and delta tend to 0. So taking limits as x tend to 0, we have dy dx equals dy dt times dt dx. This is referred to as the chain rule. dy dx equals dy dt times dt dx. Chain rule. dy dx equals dy dt times dt dx. We explain the chain rule by an example. For example, take a function of x equals y equals 4x squared minus 3x whole cubed. Here, either the derivative can be calculated by solving first algebra expression for x squared minus 3x whole cubed and apply power rules, or apply chain rule to get the derivative. So, try first by solving the expression y equals for x squared minus 3x whole cubed equals 64x to the power of 6 minus 144x to the power of 5 plus 108x to the power of 4 minus 27x to the power of 3. Y equals for x squared minus 3x whole cubed equals 64x to the power of 6 minus 144x to the power of 5 plus 108x to the power of 4 minus 27x to the power of 3. Therefore, dy dx equals 64 times 6x to the power of 5 minus 144 times 5x to the power of 4 plus 108 times 4x to the power of 3 minus 27 times 3x to the power of 2 equals 384x to the power of 5 minus 720x to the power of 4 plus 432x cubed minus 81x squared. Now apply chain rule dy dx equals dy dt times dt dx. The function f x equals y equals for x squared minus 3x to the power of 3. Let us assume t x equals for x squared minus 3x, and then t dashed x equals dt dx equals 8x minus 3. And function of t equals y equals t to the power of 3, and f dashed t equals dy dt equals 3 times t squared. We apply chain rule. Dy dx equals dy dt times dt dx. Therefore derivative dy dx equals dy dt times dt dx equals 3t squared times 8x minus 3. Now replace t x by 4x squared minus 3x to verify the result calculated earlier. Therefore equals 3 times 4x squared minus 3x squared times 8x minus 3 is equal to 3 times 16 times 4 minus 24x to the power of 3 plus 9x to the power of 2 times 8x minus 3 equals 48x to the power of 4 minus 72x to the power of 3 plus 27x to the power of 2 times 8x minus 3 equals 48x to the power of 4 times 8x minus 72x to the power of 3 times 8 times plus 27x to the power of 2 times 8x minus 48x to the power of 4 times 3 plus 72x to the power of 3 times 3 minus 27x to the power of 2 times 3. Simplifying further equals 384x to the power of 5 minus 720x to the power of 4 plus 432x cubed minus 81x squared. Chain rule. Dy dx equals dy dt times dt dx. It is important to observe the function carefully before we start differentiating. If the function is pure algebraic function, it is better to simplify the function in the form such that each term in the expression is in the form of x to the power of n. In some cases, you may need to apply product rule or quotient rule. Chain rule is very useful when the function has many part and mixture of algebraic term, trigonometry term, exponential terms, etc. When should the chain rule be used? First rule is if the expression is made up of brackets and power. For example, y equals 2x plus 5 to the power of 4, here we let t equals 2x plus 5, and y equals t to the power of 4. Next, for example, y equals square root x to the power of 3 plus 6, here we let t equals x to the power of 3 plus 6 and y equals t to the power of 1/2. Another example, y equals sine cubed of x, here we let t equals sine x and y equals t cubed. Another example, y equals sine of x squared plus 5x, here we let t equals x squared plus 5x and y equals sine t. Please note, in case of more complex expressions, the derivative may use two or more rules of differentiation, such as product rule with chain rule, or quotient rule with chain rule. Standard derivative of chain rule. Note function f equals y and derivative f equals dy dx. For the function sine of kx, the derivative is k times cosine of x. For the function cosine of kx, the derivative is minus k times sine of x. For the function tangent of kx, the derivative is k times sec square of x. For the function sine of function of x, the derivative is f dashed of x times cosine of x. For the function cosine of function of x, the derivative is minus f dashed of x times sine of x. For the function tangent of function of x, the derivative is f dashed of x times sec square of x. Implicit functions. An implicit function is one in which a relationship between, say, two variables x and y is given, without having y as an explicit or clearly defined function of x. Note, in y equals 3x squared minus 7x plus 1, y is given as an explicit function of x. But in y squared minus 3yx equals x squared, y is not given explicitly as a function of x. An implicit function involving y and x can be differentiated with respect to x as it stands. Let's find the gradient of y squared plus 4x equals 6x squared at a point 1, 1. Differentiating each term with respect to x. d dx is squared plus d dx for x equals d dx 6x squared. Or dy is square dy dx plus d dx for x equals d dx 6x square, or 2y dy dx plus 4 equals 12x. Note that we have rearranged d dx y square using the chain rule. D dx y square equals d dy y square. Dy dx to enable y square to be differentiated with respect to y. Therefore dy dx equals 6x minus 2 divided by y, and gradient at 1, 1. Therefore dy dx equals 4. Please note, for the function f, x equals y equals 1 divided by square root of x, we have calculated earlier, from first principle, the derivative d dx 1 divided by square root of x equals minus 1 divided by 2x times square root of x. If we rewrite the function as y square equals 1 divided by x, note, we differentiate d dx y square equals d dx 1 divided by x as implicit function. It is 2y dy dx equals minus 1 divided by x square. Replace y equals 1 divided by square root of x, or 2 times 1 divided by square root of x dy dx equals minus 1 divided by x square. Or dy dx equals minus 1 divided by 2x times square root of x. Example: find the gradient dy dx in term of x and y and its value at 2, 2. Of y cubed plus 6x equals 3x square. Solving for y cubed plus 6x equals 3x square, we differentiate each term with respect to x. Or d dy cubed dy dx plus d dx 6x equals d dx 3x square. Or 3y square dy dx plus 6 is equal to 6x. Therefore dy dx equals 6x minus 6 divided by 3y square. And gradient at 2, 2. Therefore dy dx equals 1/2. Example: find dy dx in term of x and y of 3y square plus 2y plus x, y equals x cubed. Solving for 3y square plus 2y plus x, y equals x cubed, we differentiate each term with respect to x. d dy 3y square dy dx plus d dy 2y dy dx plus d dx x, y equals d dx x cubed. Or 6y dy dx plus 2d y dx plus in bracket y d dx x plus x d y dx equals 3x square. Or 6y plus 2 plus x d y dx equals 3x square minus y. Therefore dy dx equals 3x square minus y whole divided by 6y plus x plus 2. More example. To understand, find the equation of the tangent and the normal to the curve 3x square plus 2y square plus x, y equals 13 at the point 1, 2. Before we proceed, let's verify whether the point 1, 2 lies on the curve. 3x squared plus 2y squared plus xy equals 3 plus 8 plus 2 is equal to 13. Yes, it does. We differentiate. 3x squared plus 2y squared plus xy equals 13. Each term with respect to x. dy dx 3x squared plus d dy 2y squared dy dx plus d dx xy equals d dx 13. Or 6x plus 2y dy dx plus y d dx x plus x dy dx equals 0. Or 6x plus 2y plus x dy dx plus y equals 0. Therefore dy dx equals minus 6x plus y whole divided by 2y plus x. We continue with example, find the equation of the tangent and the normal to the curve. 3x squared plus 2y squared plus xy equals 13. At the point 1, 2, or gradient, dy dx equals minus 6x plus y whole divided by 2y plus x. At the point 1, 2 equals minus 12 divided by 5. The equation of the tangent. At the point 1, 2, y minus 2 equals minus 12 divided by 5 times x minus 1. Or 5y minus 10 equals minus 12x plus 12. Or tangent is 12 times plus 5y plus 2 is equal to 0. Remember, the slope of the normal equals minus 1 divided by slope of the tangent equals 5 divided by 12. The equation of the normal is y minus 2 equals 5 divided by 12 x minus 1. Or 12y minus 24 equals 5x minus 5. Or normal is 5x minus 12y equals 19. Thank you very much for watching our video. Please subscribe our channel for other videos.